And we are back, just in time for Samuel telling us about, well, what is time anyway? Go.
Hi, my name is Sam Bishop, and I'm a freelance software developer and a bit of a nerd for anything time or space related. If you want to talk in depth about anything I cover in this presentation, feel free to contact me at any of the places I can be found online. So what is this time thing anyway? Well, time as a basic concept is the passage of events from the future through the present and into the past. In practical use, it's the measurement of this passage itself or the recording of events against this passage. Clocks and calendars are the tools we have to measure this passage of time, and starting with calendars from about 10,000 years ago. Based solely on the motion of the moon, these were lunar calendars originally, and by 3000 BCE, these had turned into lunisolar calendars in many civilizations around the world, adding extra days to keep it roughly in line with the solar seasons. By about 2500 BCE, the ancient Egyptians were using the first solar calendar, and this was based on measurements of the stars in the night. In 238 BCE, Pharaoh Ptolemy III decreed the leap years would have an extra day every fourth year in order to keep it better in line with that solar calendar. And in 46 BCE, Julius Caesar created the Julian calendar. In 22 BCE, Roman Emperor Augustus enforced Ptolemy's earlier decree after 216 years, which just goes to show that even if you're a god king, no one likes it when you change the calendar. But someone did change the calendar and get away with it. That was Pope Gregory XIII in 1582 on February 24th. He reformed the Julian calendar, creating what will eventually be called the Gregorian calendar. On to clocks. So sundials were the first tools we had to measure units of time smaller than a day. I'm going to skip ahead a bit here because this is a talk about modern timekeeping. You don't need a history of clepsydra. By the year 1000, we had the first mechanically regulated clocks appearing in places around the world, such as China and Europe. And by the year 1500, we had clocks appearing in wealthier households. 1657 saw Christian Huygens, a Dutch astronomer, build the first ever pendulum clock. And in 1761, John Harrison submits the H4 chronometer for the English Parliament's Longitude Prize, representing a significant advancement in navigational timekeeping. In 1921, we had the invention of the short synchrotome, which was the most accurate ever pendulum clock. And in 1927, we had the invention of the quartz clock by Marison and Horton. In 1949, we had the first atomic clock. Now, this was actually an ammonia-based atomic clock, and while it did keep good time, it was actually not more accurate than the existing quartz clocks that were in use at the time. 1955 was a big year for atomic timekeeping. We have the first ever cesium atomic clock. We had the first commercial atomic clock, the Atomicron, and that was also a cesium atomic clock, which means they became commercial products in under a year. The Greenwich Observatory began keeping Greenwich atomic time using one of those atomicrons. I believe it was unit number 207. And the International Time Bureau also begins keeping an atomic timescale, also with an atomicron. In 1956, we redefined the length of a second, having finally agreed that the second based on the Earth's rotation wasn't good enough. And we redefined it as a fraction of a tropical year, which is astronomically measured from one vernal equinox to the next. We move on to 1958, where we precisely measured the hyperfine transition of cesium. This will become useful in a moment. In 1960, we have the first satellite-based navigation system when Transit 1B is successfully launched, Transit 1A having sadly failed to launch. And this is in 1960, about the time rubidium atomic clocks are developed as well. But because they came out of commercial research, it's a little bit fuzzy exactly when they started building them. 1967 is when we finally decide that this whole atomic clock thing is the right way to go. And we redefine the second to be a specific number of those hyperfine transitions of a specific type of cesium atom, cesium-133. 1969 not only saw the moon landing, it saw the BIH replace their older atomic timescale with TABIH, TA being short for the French Temps Atomiques, and this soon turns into TAI, which is short for Temps Atomiques Internationales, or International Atomic Time, as most of us will probably know it, and that is the last I'm going to butcher any French acronyms. 1972, atomic timekeeping entered the mainstream when the Universal Coordinated Time, or UTC, was adopted formally based on TAI plus 10 seconds. 1972 is also the only year we've ever had with 2 leap seconds. 1977 saw the adoption of adjustments to compensate for relativistic effects when combining all the clocks that made up TAI, and the original timescale, because timekeepers tend to be very consistent people, continues to this day as free atomic time with another one of those French acronyms, EAL. I do not have enough time to go deeply into satellite navigation, so let's just cover the concept. So there are a number of satellites always orbiting overhead, sufficient in number that you can always see several of them at any one time. The old ones actually look like the ones on the right there. And the old ones use cesium atomic time standards like you can see in the top right. More modern ones, like the European Galileo satellites, use hydrogen masers like you can see in the bottom left. And these satellites broadcast out radiating time signals into the universe, mostly aimed downwards for our benefit. And when they arrive on the surface of the Earth, the curved wave fronts can be intercepted by our antennas, combined, coordinated, and through a complicated process of triangulation, we can work out where the satellite thought it was at the time that signal was broadcast, and what time it thought that was that it broadcast it. And by combining all of this information, we can actually generate a geometric triangulation that gives us a position with a certain amount of accuracy, like a very, very fancy, complicated version of basic geometric triangulation that you can do with a protractor. Now, on the next detail. So, watching the skies. Astronomers do this a lot, and after a while they began to notice something was funny. So in 1899 they established the International Latitude Service, which began carefully measuring the Earth's rotation. And in 1962 that service was replaced by the International Polar Motion Service, and in 1988 the International Earth Rotation Service, or IERS, whose logo is on the left, takes over the duties of the IPMS. And what exactly they were doing was they were measuring the Earth's wobble. Because as they took precise astronomical measurements, things would move a little bit year to year. They kind of got fed up with it, so they wanted a way to compensate. So they began measuring, very precisely. And then after a while they began to notice something else other than the fact the Earth wobbled. They noticed that the Earth didn't rotate the same. So they began to document the rotational instability. You can see here this is the last 20 years. I didn't bother going back to the original 1899 data, which is available actually. And these charts show that the Earth does not actually rotate stably, which they noticed very quickly. So they had to start charting this out, and we started compensating for it when we were keeping track of time. And as we began developing atomic clocks, we started to adjust for it automatically, which is where we get the leap second. The dreaded leap second. So the leap second happens simultaneously around the world. This can be a bit unintuitive for most people. So while the leap second is introduced at the end of the day, UTC, it'll actually happen at a different place every time as you move around the world. So last leap second was at just before 8 AM in Perth and just before 10:30 AM in Adelaide, and so on through various time zones. And not only does this break a lot of things like precision time stamping between distributed systems, it also is just basically not handled very well by a lot of systems. It's pretty easy to just assume that a second is 59 of them plus 0 next minute. So Unix and Linux systems frequently just repeat that last moment in time to fill in the gap, and some just don't know how to work with it at all, such as Wolfram Alpha on the left, which I checked last night. Now let's have a look at Python. So the standard library doesn't do very well with leap seconds. It's not really built for this. So if we take a second just before the leap second and we add 1 second to it, we don't get the right time, we get 2 seconds later. And if we try to parse a valid date time that would actually represent the leap second, the standard library doesn't know what to do with that. Pendulum doesn't fare much better. It makes the same mistake skipping over the leap second, and it makes a similar mistake parsing the leap second. So let's look at a library that does actually successfully handle leap seconds. We have AstroPy. So AstroPy does handle this because it was built for and designed to deal with a number of complicated astronomical calculations. Getting the time information right is absolutely critical for it to do its job. So out of the box, with no additional configuration, it handles these correctly. This is pretty much, table stakes for a good astronomy library. And it is a good astronomy library. It's pretty much the reference one, at least as far as Python is concerned. So what do you do if you don't want to use an astronomy library to handle all of your times? Well, if you're Google in 2008, you decide to come up with this cool concept called leap second smearing. So this particular image is from a Red Hat blog from the last leap second, and it demonstrates how everyone is able to do this with just regular NTP daemons. But the principle is the same. What you do is you, instead of jumping suddenly, you adjust it very slowly in very small steps, a little bit before and a little bit after. So instead of having one big 1 second jump, you break that 1 second jump up into a lot of very small pieces and spread it very far out across the day. And this way there's less disruption for systems. But it still isn't really doing things the right way. Now, let's get over to reference frames, because modern timekeeping involves a lot of reference frames. Reference frames are kind of the most important detail when dealing with modern time systems. They date back to Einstein and relativity, hence reference frames. And we have so many clocks in space now and so many things based on those clocks that reference frames are crucial. So those reference frames are all coordinated through a number of complicated formulas and a number of very fastidious record-keeping processes. But if you know how it all fits together, it's actually pretty simple. They all relate, they all have equations, they all have records, and if you use a library like AstroPy, you can convert between them fairly easily. And why would you use all of these? Well, for science. Things like radio occultations from satellites orbiting Saturn. This is from the Cassini spacecraft. They were able to measure the density of Saturn's rings by using radio occultations. This requires precision measurement of the timing of the arrival of those radio waves, because they're scattered and absorbed and retransmitted a number of things through the rings. And in a more extreme example of this, you have them measuring the interior of Rhea, another one of Saturn's moons, which was determined to be a solid object based purely on doing this kind of radio occultation data. So they worked out that it was a solid moon with a thin crust. Well, you might be saying to yourself that this doesn't matter a lot to you. So let's get to some more information that is a bit more related to what we do as programmers. So when you're working with dates and times, there's a number of things that are able to really trip you up. Things like the leap seconds. So for leap seconds, they're only known about 6 months in advance. So when they do happen, and they aren't deterministic, so you do not have a guarantee of when the next one will be, you are going to have to know at that point. Anything after that, you don't know. So every 6 months into the future gives you a certain degree of uncertainty as to whether there will be a leap second or not. So if you have to time something in the future precisely, you need to decide whether you're going to measure it clock time chronologically or against a calendar calendrically. On the same point, future time zone changes aren't deterministic. Governments can decide to change these on a whim. So if you need to compensate for this, one good way is to store the location that the event will take place and also store the time that you made that entry. And that allows you to compensate for the majority of time zone changes. A good historical one here is that Unix time was not properly defined before the 1st of January 1972. So for the first 63 million seconds of Unix time, it isn't actually deterministic. And there isn't any standard leap second smearing between vendors, which is the other modern problem that will trip you up if you have a fairly large system. So if you do need to have precise ordering between libraries and timestamps and multiple clouds and things like this, you need to make sure that you use the unsmearing libraries or algorithms that each vendor documents. Google, Amazon, Microsoft, they all have well-documented information for this. And on that point, my top 6 choices for Python libraries: if you're going to be doing 99% of the things, Pendulum will do the job. AstroPy, if you need that last 1%. Dateutil is awesome. Dateparser will handle just about anything. Django time zone field, if you are trying to store any time zones in a Django app, have a look at this. And if you'd like to learn more, there is a number of really great resources out there, including Stack Overflow and Wikipedia. So are there any questions?
We have time for one question. One question we had was, what is special about a rubidium clock?
It's cheaper. They aren't as accurate as cesium atomic clocks, but they are cheaper and able to be miniaturized better. You can actually go and buy a rubidium atomic clock that fits on a Raspberry Pi for about $1,500 US. Yeah, it's about the size of a matchbox.
Okay. Well, are you going to have a minute or two after your talk to chat to people in the hallway?
Yeah.
Wonderful. We are now exactly at time, but now we have a whole hour in which to stretch our legs, get some sunshine if the sun is out in your time zone, and we will see you with some more talks in about an hour. Bye.